Hello everyone, it is a really pleasure to be here. My name is Rui Fu, and I am a staff software engineer at StreamNative. Today, I'd like to share a topic about managing data streaming infrastructure in the age of AI by simplifying tooling and integrating with MCP. Before we dive in, here is a little bit about myself. I have been working with Apache Pulsar, serverless platform, and cloud infrastructure since I working at StreamNative. I've been fortunate to contribute to open source projects like Function Mesh, Pulsar Resource Operators, and StreamNative MCP Server. Here is our plan for the next half hour. First, we will talk about the two big challenges in streaming infrastructure today, mainly on StreamNative Cloud. Then, we will explore how we are solving them at StreamNative. One part with better tools for humans, and one part with better interfaces for AI. We will wrap up with where this is going and how you can get involved. Okay, so let's start with the pain points. From our perspective, there are two primary challenges in managing data streaming infrastructure today. The first is fragmented tooling. Anyone who works with multiple CLI tools knows this pain. The second is the shift to agentic AI, which introduces a new requirement for how our infrastructure needs to get interacted by the large language model and AI agent. Managing model data streaming infrastructure is a fragmented reality, especially at StreamNative Cloud. Look at this diagram. It captures a typical landscape. We are constantly juggling multiple command line interfaces, configurations, and workflows. Whether it is Pulsar Cattle for the Apache Pulsar, Kafka CLI for Apache Kafka, or even KCCTL for Kafka Connect, SNCTL for StreamNative Cloud, or tools like Terraform and other operators for deployment and management. Each technology comes with its own set of tools and paradigms. This fragmentation creates complexity, increases the load on engineers, and ultimately slows down development and operations. At the same time, we are seeing a big shift in AI. It is not just about asking questions anymore. Now, AI agent can reason, plan, and take actions. The shift means new interactions are needed between AI agent and our data streaming infrastructure. But they can only do that if they can actually connect to the system that matter, like your data streams, your brokers, your environment. So the challenge is, how do we let AI act, but in a way that it is safe, structured, and reliable? So this is where MCP comes in, the Model Context Protocol. Before we jump into the details, I will spend 1 or 2 minutes to talk about what is MCP. As I mentioned, MCP stands for the Model Context Protocol. It is designed as an open standard that aims at standardizing large language model to and from data and tools interaction. One simple understanding is thinking of it like the USB-C, but for AI and infrastructure. It gives AI agent a consistent way to discover and use capabilities, like reading a topic or provision a Pulsar I/O connector, without having the hard code anything. MCP standardizes the interface between models and tools so they can speak with the same language. One of the key things MCP solves is the M times N problem. In a traditional integration approach, if you have M different AI models and N different data sources or even tools, like different databases, cloud storage, or a GitHub repository. You often need to build custom integrations for each combination. This results in m times n connections. For example, with 3 models and 3 data sources, you will need 9 customer integrations, as shown on the left. But with the MCP approach, your integration each model once with an MCP client and each data source once with an MCP server. This reduces the total number of connections to m plus n. So in our example, that is 6 in total connections, which is less than 9. It is like replacing 9 cables with 1 universal port. Another similar technique is LSP, which solves the m times n problem for programming languages and the IDEs. So now that we understand the challenges and why MCP matters, let's take a look at how we are applying these ideas at StreamNative, starting with human operators, then moving to AI agents. And we built 2 key components. First, the SNCTL, a unified CLI that simplifies how people manage Pulsar, Kafka, and StreamNative Cloud. Second, the MCP server, which exposes the same capability to AI agent, or even more. Let's start with the simplifying tooling. As we discussed, engineers today are switching constantly between different CLI tools, just as the image showed. So we thought, what if we just had one CLI that did it all, regardless of whether it was for Pulsar, Kafka, or cloud resources? Our answer is SNCTL V1, a single command line interface that unifies Pulsar, Kafka, and StreamNative Cloud management. With SNCTL V1, you no longer need to switch tools or contexts, and you will gain the unified user experience on StreamNative Cloud with SNCTL V1. As you can see in the example here, you can use SNCTL Pulsar subcommand to interact with Pulsar APIs, and with the SNCTL Kafka subcommand to interact with the Apache Kafka APIs. Let me briefly go through the newly released SNCTL V1's key capabilities. As mentioned before, it provides fully support on client and admin operations for Pulsar and Kafka protocol. It also manages connectors like Pulsar IO connectors, Kafka Connect, and as well as for the schemas and the StreamNative Cloud infrastructure. And it has powerful context switching, so you can go from managing a cloud cluster to a local test environment, or even an external Kafka or Pulsar cluster with a single config. For example, you can manage different services contexts, including StreamNative Cloud clusters and external clusters, all within a single configuration and workflow using SNCTL context subcommand. This allows users to easily switching between managing different clusters and environment. So that is the first half, by simplifying tools for people. Now let's look at the second half, integrating AI with streaming infrastructure. And this is where the StreamNative MCP server comes in. The StreamNative MCP server connects agentic AI to your data streams. It acts as a bridge, exposing a set of capabilities that AI agent can discover, understand, and invoke. Then the result is an AI-ready interface for your streaming system. So when an AI agent needs to produce a message, or check logs, or even read from a schema registry, it doesn't need to know your internal API. It just uses the right MCP tool. Now let's take a closer look at what kind of capability the MCP server actually gives to the AI agent. So there is three main categories. First, we have tools. These are actions an AI agent can perform, like producing a message, reading from a topic, or checking broker healthy. Second, we expose resources. This is a read-only information, like a list of tenants, namespace, or topics. It gives the agent the context it needs to make decisions. And third, we have prompts. These are like templates or workflows that guide the AI through more complex interactions. For example, a prompt might help it fill out the right values for provisioning a cluster or even configuration of a Pulsar I/O connector. These three types gives structure to what the agent can see and do. They are building blocks of the agent interaction with the infrastructure. So how does this actually play out? Here is a common example. A user asks the agent how many events per second are flowing through topic X right now. The agent reasons through the question, select the right tool, maybe the Pulsar admin topic tool, and use that tool to get the topic status. Then the agent formats the answer and responds to the user, all without even knowing the Pulsar API itself. This is the reason and act pattern. So the agent reasons and make decisions, and the MCP server takes care of the action. Now that we have covered the concepts, let's take a deeper look into the design and capabilities of the StreamNative MCP server. Here is one problem we faced earlier when we building the MCP server. Imagine we already have the API specifications for each services, like for Pulsar, for Kafka, and for StreamNative Cloud. And there are a lot of auto-generators of MCP server for OpenAPI or other API specification, and it makes us thinking of the straightforward approach by automate generating the MCP server from the API specification. But the reality is, if we expose every single Pulsar, Kafka, and StreamNative Cloud API as a one-to-one MCP tool by the auto generator, we will end up with like over 300 tools. The 300 as a number is completely unmanageable for both AI agent and humans. AI model don't perform well when faced with too many options. Some large language model based clients like Cursor with some models may even ignore tools past the first 14. And even worse is, many of these auto-generated tools would come with poor description that are hard for large language models to understand. Editing hundreds of them manually isn't scalable either. So we realize that we need a better strategy, something that keeps the interface lean and large language model friendly without losing the functionality. That is why we use a scalable design. Instead of one tool per API, we group related actions under parameterized tools. For example, the Pulsar admin brokers tool can handle multiple operations based on the input parameters, such as listing active brokers, checking health status, or managing configurations, all depending on the parameters provided by the AI. We also refine each tool's description to make it easy for large language model to understand, as well as the examples. The result is a clean set of about 36 tools, which are powerful and manageable. Here is a screenshot from Cloudy showing how these tools are surfaced to the AI with description name and well-structured parameters. The AI can reason effectively and choose the right tool for the job. Of course, with great power comes great responsibility, and security is built into the MCP server from day one. It uses service account to identity, RBAC for permissions, read-only mode for observation-only scenario, and two whitelists so that the agent only sees what you want it to see. It also validates every input and every output, so you are not passing sensitive data back and forth. And we're also working on adding the OAuth2 support for integration with StreamNative Cloud auth system. So for MCP server, the bottom line is like, yes, AI get access, but under your control with full audit logging and safety. Now, what about connectors? Unicorn is StreamNative's unified framework for connectors. It supports Pulsar IO and Kafka Connect, and let you to interact with external systems like database and cloud storage. Now the power comes in how the StreamNative MCP server integrates with the Unicorn framework. Because the MCP server is designed to understand Unicorn, it means the rich ecosystem of Pulsar IO and Kafka connectors become directly accessible to your AI agent. The MCP server can expose these connectors as capability, potentially as streams in Kafka or Pulsar. This enables an AI agent to leverage an existing connector to access data from hundreds of external systems, whether it is pulling real-time change events from a database, consuming messages from a different streaming platform, or even syncing data to cloud storage. The significant advantage here is that the AI agent can perform these tasks without requiring customer integration code for each specific data source or sink. Unicorn provides the unified bridge, and the MCP server makes the bridge actionable for the AI. This integration is key to building real-time enterprise AI agent that it can tap into existing connectors to instantly access data from numbers of sources and sinks without custom code. It is truly extend the reach of your AI agent across your entire data ecosystem. We will also integrate Pulsar functions into the MCP server. Pulsar functions and the underlying serverless framework are key components for building real-time data processing pipelines directly within your streaming platform. What we have done with the MCP server is enable AI agent to interact with this capability, providing a natural language interface for the entire function lifetime. The entire function life cycle. That means AI agent can develop, deploy, and manage Pulsar functions directly. From tasks like develop a function, the AI agent can utilize the predefined prompts or even the large language model's own programming ability to generate the necessary configuration or code and submit it via MCP2. Additionally, with the login tool provided by MCP server, it helps the AI agent to lively debug the running functions as well. But the integration goes even deeper, and this is the truly exciting part shown in the image. Leveraging the capabilities provided by the serverless framework, the StreamNative MCP server can dynamically discover deployed Pulsar functions and expose them as invocable MCP tools for other AI agents. This is what we call the functions as tools feature. Once a function is deployed, it becomes a callable MCP tool with input topic schema attached to the tool's parameters. So now your business logic is part of your agent's toolbox. The MCP server allows agent to manage StreamNative Cloud resources, such as creating a classic engine serverless cluster or an Ursa engine dedicated cluster. It also allows agent to manage Pulsar Kafka resources, like creating tenant namespace, topics, and managing the partitions, even if these are across multiple clusters. All these operations respect the RBAC permissions, so the agent can only perform allowed operations. This enables safe automation infrastructure management. Last but not least, we let AI subscribe to your streams. With SSE and streamable HTTP, an AI agent can receive real-time events and reason and act on them. That means this allows AI to listen to the streams, enabling real-time agent behavior based on the latest data flowing through the platform. So let's bring it all together and talk about the real impact. For human operators, SNCTL gives you one place to work with Pulsar, Kafka, and StreamNative Cloud. No more switching between CLIs or learning different flags. It brings a consistency and simplicity to daily operations and makes scripting and automation much easier. For AI agent, the MCP server exposes a structured and secure interface to your streaming infrastructure. Agents can act in real time and managing the pipelines and resources and interact with the connectors, all through natural language and all governed by permission and policies. Looking forward, we are integrating the MCP server with Ursa. Ursa is the StreamNative's next generation Lakehouse native data streaming engine. Its core design brings together real-time streaming data and historical lakehouse tables like the iceberg and the Delta Lake. With MCP plus Ursa, your AI agent can unify real-time and historical insights, like answering questions that span both recent events and long-term trends. So let's take a step back and look at the big picture. We have built two key components that complement each other. One is SNCTL, the unified CLI that simplifies how human operators manage the streaming infrastructure. The other is the MCP server, which connects the same infrastructure to AI agent in a clean, secure, and standard way. Together, these tools don't just reduce complexity, they open up new possibilities, as we've already been surprised by internal usage of the AI agent with StreamNative MCP server. So, if today's talk sparked your interest, we'd love for you to try it out and join us with this journey, starting by downloading the SNCTL version 1.1. It now includes the unified CLI as well as the embedded MCP server, which means you can try to start the StreamNative MCP server directly from the SNCTL right away. If you're interested in the StreamNative MCP server, you can also explore the open source StreamNative MCP server on GitHub. We've got some demo videos on the StreamNative Academy YouTube channel as well to walk you through some examples. And these demo videos are made by our teammate Dustin. And if you are curious about the border region, our community is a great place to get involved. And also your feedback helps us to shape what is next. So don't hesitate to reach out if you have any questions. And that is the end of my presentation. Thank you for your time and attention today. I will be happy to answer any questions from the platform. Thanks.
All right. Thanks, Ray. Thanks so much for sharing your experience, expertise, the contribution to building out the MCP. Super appreciated. And yeah, thanks so much for bringing that. All right, great. Now we're gonna take some live questions from the audience. So, all right, we got two questions. It seems that you answered the first one. Um, I'm still gonna read this out loud just in case people haven't seen that yet, and if there's anything you want to elaborate more on. So the first question, can you explain more about how functions with MCP server? Does it mean that my function logic can be exposed as tools to agents?
Yeah, so I will firstly repeat my reply. So this is a really a good question because like we said, the functions as a MCP2 is like a highlight of our MCP server, and so we just to expose our running function logic to be MCP2s, so the MCP client can connect to the MCP server and construct the messages to the actual function as the MCP2 core. And actually, we did some schema conversion. So as we understand that each MCP2 requires some basic concept that like the description and also the parameters. And so like we actually gather the schema from the function's actual input topic, and we convert that to the MCP2's parameters so that our MCP server can construct the real, actual message to that function. And this is how we like building the MCP to build to expose the running functions as MCP2s. Yeah. So I hope this answers the question. Yeah.
Yeah, thanks so much for the elaboration. All right, great. So the next question from Peter. Can you apply different sorts of access control lists on the different bucketized MCP tools you have, having read write controls? Like even for instance, like no, I won't let you do this or that.
Okay, so this is another very good question because we see the security like in the MCP area is very important. So actually, I will directly answer the question. We are actually control the ACLs from our RBAC system. So you can like control the real actually access control from the service account provided by the StreamNative Cloud. And so you can utilize, you can see that I want this service account only can do something to the actual Pulsar cluster or even the tenant and namespace. So this is how we introduce the ACL with RBAC. And another part is that we actually implement some flags to the MCP server, like the read-only flag and also the features flag. So with the read-only flag, you can choose only the MCP server can only read the can only call the read tools to each the resources. And for the features, you can control which kind of tools the MCP server could be used, could be exposed to the MCP client. So this is kind of what we are trying to solving the problem right now. But as the StreamNative MCP server is still a very new thing, and the MCP area is also a new stuff for us. So we are still trying to contribute our own understanding to the community. Yeah. So I think this answers the question. Yeah.
Awesome, awesome, great, cool. All right. So that's two questions we got from the audience. Any more questions? We still got about 1 minute left. If anyone wants to pick raise brain a bit more. All right, awesome, cool. Okay, great, fantastic session. Thanks so much, Ray, again for your time and your expertise. For the audience, please feel free to do the survey to win prizes, or contact us in the main stage in the lobby to get the network started. If no more questions, we're gonna give everybody 1 minute back, and I'll see everybody else. See you guys in the next sessions, which starts in about 1 minute. All right.
Okay. Thanks, Cassie.
Awesome. Thank you. All right, bye.
Bye.